Thank you everyone for coming. I'm Shehryar, this is Frank, Mascarich, and Tung. And we are PhD students or graduate students in the lab, and we'll be giving a presentation on multimodal mapping. Thank you all for coming. But if some students want graduate credit, you can sign up on this sheet. This sheet would be here. And Frank would be starting with the presentation now.
Welcome. As Kostas had mentioned earlier, one of the key requirements of a robotic system to be able to function in a real-world environment is perception. It's one of the biggest challenges facing our robots today. To accomplish perception, we have a number of different tools. One of the most important, obviously, is our cameras, both monocular and stereo. We also have inertial measurement units, which provide rotation and position tracking. Lidar is one of the more recent trends and provides high detail, high fidelity maps for robots to navigate, as well as time-of-flight cameras for short distance perception, seeing either pedestrians or, in the case of our own robots, mapping the environment with a lightweight sensor that can fly for long periods of time. And as well as application-specific sensors. As shown here is a radiation sensor that we're working with right now. These 5 tools provide the robot with perception capabilities, which allows us to accomplish the goals of localization, mapping, and general autonomy tasks. These are our 2 main workhorses in the lab. On the left is a drone that features a stereo camera, these cameras here, as well as a picoflex time-of-flight sensor that provides the local short-range mapping capabilities. On the right is our heavy lifting drone, as you can see it right here. It has a Lidar on top, the same stereo camera system, and some LEDs to provide illumination of the environment. These 2 drones are built from completely off-the-shelf components. Anyone can go to Amazon and purchase similar components. Although, as Kostas mentioned, that there are some wait times for things like Lidar and time-of-flight sensors. They're very popular. Everyone's trying to get them. And we are fortunate enough to have them here in our lab. However, as we progressed with our research, we realized that there are certain tasks that we need a custom system for, and this is one of the systems we developed inside our lab. We call it the M3U, which stands for Multi-Modal Mapping Unit. It is, number one, first of all, is synchronizable. It synchronizes cameras with IMU and any other application-specific sensor we would have to incorporate into our robot. Second, it's extendable. It's shown here, it's in a stereo camera configuration with a carbon fiber frame and a 3D printed mount that fits on board the drone, similar to how the camera is mounted here. In this configuration, it also features 2 LEDs for illuminating environments, visually degraded environments, particularly for dark rooms. The LEDs are synchronized with the shutter of the camera for 2 reasons. One, the synchronization, or turning off the LED for about 90% of the time saves a ton of power. Second, turning off the LED for about 90% of the time allows us to run the LEDs a lot hotter than we could otherwise. If you leave the LED on for long periods of time, it's going to heat up. And actually, these are so high power LEDs, such high power LEDs, that we've melted a few by leaving them on for too long. Flashing them conserves that power and keeps them cool enough for us to run them much hotter than we could otherwise. So right now it uses 2 visible light cameras. However, we could extend it to other cameras like IR cameras or UV cameras. We could also, it's also an extendable system in that we can add multiple cameras. It's an N camera system, so we can trigger it like on the bus. We can trigger up to 12 or 16 cameras if we need to. As well as it can also incorporate application-specific sensing, like radiation sensors. I'll get to that in a moment. This is the overall system diagram of the M3U. It consists of an ARM microcontroller that triggers our IMU and the N cameras that we have connected, as well as the LEDs in this case. The ARM microcontroller sends triggering timestamps to the high-level controller, which is an Intel NUC. As Kostas mentioned, it's an Intel processor that is basically a laptop in a very small form factor and specially designed to fit on board a drone. from our timing diagram here, this is what the M3U allows us to accomplish. We can have precise triggering of both the IMU and the camera, and because we have this control over the triggering of sampling on the IMU, we're able to trigger the IMU in the middle of the camera shutter time so that we can correlate the exact precise measurements from the IMU with a particular camera frame, which results in much more robust and efficient localization. Here's a short video of the M3U in action. As you can see, the flashing lights are somewhat synchronized with the camera that's recording it. On the right, you have a dense real-time map from our time-of-flight sensor that provides high-fidelity mapping of the environment. And on the right here, it's a lower fidelity but much more memory-efficient mapping technique that we use for our path planning algorithms. These are some handheld results, actually in the hallway just outside this room. As you can see, we accomplished high-fidelity mapping with very little drift, both in across the entire hallway and in the detail of the structures inside the tunnel. You can see these are the visible light images, and these are the point cloud images from both stereo and the time-of-flight sensor. So stepping back, as I mentioned before, one of the more critical pieces of hardware that we have to localize with on our robots are camera systems. We have both monocular and stereo, and Shehryar will be covering some of the advantages and disadvantages of each type. But for the most part, cameras are used to correlate the robot's position against a static environment. So you know the location of this edge, this corner, this object, and you can ascertain the robot's position from that image. They come in multiple modalities: visible light, IR, and UV. And there's a significant advantage to using alternative spectra. Visible light, as you might know, is a very narrow portion of the light spectrum. There's also UV and infrared, which there do exist cameras that can see in UV and infrared. Not only is it providing more images for our computer to process, but there may exist features in IR and UV that don't exist in visible light, and provides more robust localization for our robots. So as you can see in this image, the bridge is completely invisible in the visible light spectrum, but using shortwave IR, the bridge is very clear and visible. And so this, definitely IR, and we're experimenting with UV, will greatly aid us in localizing in visually degraded environments, both fog, rain, snow, and darkness.
I have a question for you.
Sure.
Are you using infrared LEDs?
Eventually, we do have them. We haven't experimented with them as yet.
We do.
Actually, we have
Oh,
on
yes,
this
that's
robot, these are LED infrared emitters, and then this small camera, the stereo camera, it can see the spectrum in NIR. So we have, and you can take a look after the presentation.
Moving on, past cameras, the next most critical sensor that we use are navigation sensors. This incorporates IMU, which is an integrated accelerometer and gyroscope. We also use magnetometers to ascertain our orientation or change in orientation in the environment. Pressure sensors are also important, although we don't go very high. Barometric pressure changes with the weather and it's a little more sensitive. Inertial sensors like gyroscopes and accelerometers come with a lot of bias and noise, but we offset that disadvantage with the advantage of cameras and the strength of their localization. Another form of sensing that we are actively exploring is Lidar. Lidar is basically a time-of-flight measurement, so you have a laser beam that's shot out towards the surface, and you measure the reflection back from that surface. The time it takes to hit the wall and come back is linearly related to the distance from that object. They come in different shapes and sizes. There's multiple beams. This Velodyne puck on top of this drone here has 16 beams that rotate in 360 degrees and gives us 360 degrees of vision. Other LiDARs are solid state and only point with a limited field of view, much more like a camera. But they all operate with the same basic functionality. Some spin around mechanically, like this one on the Velodyne, and the others are solid state, which save power and are at the moment very expensive.
I have another couple questions for you.
Sure.
The error rate that you get when you have blowing dust and sand and that sort of thing, how do you compensate for that in a LiDAR situation?
That's a very much so open research question, and I'm sure Tung will answer that once he gets to it. But the general idea is to subtract the noise from the static environment, and you know that anything that is moving should be subtracted. As long as the static objects are greater in quantity than the moving objects, localization and mapping tends to work.
Well, I was thinking about, like here in Nevada, we have some days where we have a lot of dirt moving across the road, and would a imaging system interpret data as a vehicle moving across the road, cause it to take evasive actions in the wrong place?
Potentially, that's a serious concern, and we would hope that the fusion of LiDAR and cameras together would help resolve that issue. Yeah, and that's the whole idea behind multimodal mapping. Finally, we have some application-specific sensing. In this case, is a project that we're working on at the moment. Is my main focus. We've mounted 2 pin diode detectors on either arm, opposing arms of the robot, with about a 45 centimeter stereo baseline, so they behave somewhat like a stereo camera. These are gamma ray detectors with the goal of detecting radiation in environments. There's a lot of different applications from airport or ports of entry security monitoring, as well as environmental disaster recovery or monitoring, and finally decommissioning of nuclear facilities. With the eventual goal of not knowing where a radiation source is, being able to localize that source, and perhaps use that source as an additional feature for mapping and localization. In this case, we have a microcontroller that sits up top and integrates radiation pulses over time. It sends that data to the main processor, who, while the main processor has a very good idea of where it is, it can annotate the map that it's building with the radiation data on top. And here is a short video showing the visualization of our radiation data. As you can see, the box starts off green because we don't have any radiation counts. This experiment was run with a very low power source. As the robot moves towards the source, which is located here, you'll see every now and then it'll get a more red box. So red meaning danger, more radiation, green meaning safer, less radiation. You see they slowly change over time, and as the robot knows where it is in the environment, it can annotate that data that it's getting from the microcontroller and display it on the map. So finally, one of the key characteristics of our own hardware is synchronization. And synchronization is critical to efficient operation of perception systems. IMUs and cameras are connected via USB to the main processor on board the computer, and the data arrival is completely unpredictable. Sometimes it can vary as much as 10 milliseconds to 20 milliseconds, even 30 milliseconds, and that's simply unacceptable when you're flying a drone in the air. So there are techniques to use algorithms to software synchronize the data. However, if you want true, precise triggering, you need hardware triggering and hardware synchronization, and that's what our M3U accomplishes. So I've discussed some of the hardware behind our sensor systems. Now, Shehryar and Tung will cover some of the algorithms and software necessary to process this information and make our robots work. Shehryar.
Thank you, Frank. So Frank gave us a brief overview of all the sensors we are using. So primarily, we are using cameras and time-of-flight sensors or LiDARs. So Tung and I will be giving the algorithm based on the concept behind the algorithms that we use on our systems to make our robots navigate in unknown environments, to map them. So I will be focusing on the visual part using the cameras, and Tung will be focusing on the LiDAR or the laser sensing part. So giving a brief overview what visual odometry is, that we have a camera, and as the camera moves around in the unknown environment or the world, it takes pictures. Can we use these pictures to construct or reconstruct our motion in the world? Now if you think this camera is mounted on one of our robots and it's moving around, can we use this data to reconstruct our motion? And doing this by estimation of this transformation of our robot in the world is called visual odometry. How it works is we have a camera, it acquires images. The images we acquire from a camera are usually distorted. So if you have ever taken a picture, you see on the edges there's like a circular region. This is called radial distortion. So we have to correct for that. So first step, we have to calibrate our cameras and get a camera intrinsic calibration matrix, which is usually what the focal length of the camera is, what's the optical center, what are the distortion parameters. Based on these, we first undistort our image. Next, after we get our undistorted image, we detect interest points, points which have large intensity differences or which are more robust or more characteristic. For example, if I look at this wall, the edges of the board are more characteristic rather than the wall itself. So we detect some interest points which we call features in computer vision. Then as we move along, we take more images and more images. We try to detect the same features and then match them and track them in different images. So as I move along, so this is the picture of the Da Vinci statue in front of the Knowledge Center. So I take two pictures, I detect some interest points, I track them as I move my camera around, and then by knowing the calibration matrix, I can reproject these feature points into 3D world coordinates, and then collecting them, I can estimate my motion. So stitching them together. This is what we can do with a monocular system. But for a monocular system, we have to move it around in the world to estimate our motion, and because camera gives image that is 2D, we can only estimate depth up to a scale factor. But if you look at your own perception system, that's the human eyes, you have two cameras. And if you close one of your eyes or blink one of them at one time, the image shifts a bit. This small shift in image that happens is called disparity, and we can use this to reconstruct the depth of the world. And this principle is used in stereo cameras. In stereo cameras, we not only track features from frame to frame, but between cameras as well. And as we move around, we can reconstruct or estimate the depth of features in the world. What this allows us to do is, having two images, we can create a depth map or a depth reprojection of the scene. So this is one of our visual pipeline. But this is very computationally expensive. So if you have cameras that have large resolution, you have stereo cameras, now you have two cameras, you're running them at a higher frame rate, so you're getting a lot of data, and processing this lot of data in real time on board a robot becomes a challenge. So what you want to do is to integrate your visual odometry with something else that gives you the same robustness but makes it less computationally expensive. What we do is we integrate our visual odometry with our inertial odometry. So what we have is inertial sensor, as like Frank explained. It provides us a measurement of acceleration and angular velocities in all three axes. We can simply estimate the motion by integrating both measurements. If we integrate twice for acceleration, we get our position. If we integrate once for angular velocity, we get our orientation. But as we integrate, we accumulate error. So this measurement is not reliable for a long-term trajectory, but in the short term, it's still viable. So why not mix them both? So how can we mix them? Well, we have two sensors and we have two measurements. Why not just simply first take the average? This is the simplest way. But the thing is, do we trust both our sensors equally? The answer is no. So how we can get around it? Well, we can simply weight our averages. But what can we use for a weight? Well, we know the statistics of our sensors, so we can maybe use the sensor statistics as weights and take this average. Doing this thing has an established name in the field of engineering, and we call it a filter. And one of the most common filters or popular filters that we use is a Kalman filter. So what does Kalman filter do? It takes in the model of the system, measurements and produces an estimate of the state of our system. But the model can be linear or non-linear. For example, this robot is a complex system. The model isn't linear, so we have a non-linear system. Hence, we use an extended Kalman filter, which is an extension of Kalman filter that works in non-linear models. How the overall picture works is a two-step process. We have our system model. We propagate the system or predict the state of our system by an input. In our case, we use inertial measurement units as our input to propagate the system and predict what the state of our system will be. Then in the correction step, when we get an update at a slower rate from the camera, we correct our prediction in the previous step. And then we go in a iterative manner. The beauty of Kalman filter is that we can take a number of steps before we can take another step. So, for example, our IMU runs at 200 Hertz. So, and our camera runs at 20 Hertz. So, for 10 measurements, we can run 10 prediction steps before we take a single correction step. In our system, we implement an extended Kalman filter that linearizes the model, calculates the Jacobian, uses the IMU measurements to propagate the system, and then uses the vision measurements to correct this prediction and update the covariance parameters or how much variance we have in our state and our track estimates. What is our state that I'm continuously talking about? So in our robot right now, we track the position, the velocity, and orientation. We also have some extra parameters that we keep in check for our sensor models. For example, for the IMU, we keep in check the biases, and for our vision sensors, we have the depth estimates and the bearing vectors for our features. So, merging all of this, as you can see, we have our robot flying in a GPS-denied environment without use of any external input. It can produce a 3D point cloud which is dense enough and is representative of the environment, and it is able to navigate in this 3D environment. And if I skip to the end, you can see that it has created a whole dense map as well as a volumetric map for its own representation. So, now the question is, we have this visual initial pipeline, we have our odometry, we have a 3D representation of our world. What can we do with it? So, what we have is odometry. What it provides us is with a localization in our environment. It lets me know where my robot is, or lets the robot know where it is, and it answers for the robot, where am I? The second thing is we have a depth estimation or a depth representation of our environment, which we can sort of use a map, which lets the robot know what's around me. These helps us to map and explore unknown environments where the robot had no initial idea where it was. This is our way to address one of the oldest chicken and egg problems that was referred to before, called simultaneous localization and mapping. That is, in an unknown environment, a robot doesn't know what its environment is, so it maps it, and then based on its odometry or localization data, it localizes itself in that built-up map, and then it builds a new map, and then it localizes itself. And this thing goes in an iterative manner. So, but is there a limitation to this approach? Yes, there is. First of all, odometry alone is prone to drift. For example, this is our arena where we will be doing our demo. If I walk around and I build a map using only my visual odometry, I can see that the map has skewed a bit. So this is because of the accumulation of error. You see, I'm only estimating my transform from frame to frame in the camera, and I'm also doing the same thing for the initial measurement unit. So the error accumulates over larger trajectory. Another problem with this thing is, if I'm using visible light cameras, they won't work in visually degraded environments. If I start walking into a tunnel, it would work in the beginning, but when I'm in the center or the middle of the tunnel, there's only one white spot at the end of the tunnel, so it won't work. Also, the mapping is limited by the camera's field of view. So if I want to explore the whole environment, my planning pipeline should ensure that I have full coverage, that I see every single part of it. Because I can only map parts where my cameras can see. And also, the distance that I can see and reliably have a confidence about is limited by the camera baseline or the disparity that we talked about before. So, for example, I was walking in the same environment and the camera only saw these parts. So the the ground, the field of view wasn't wide enough that it could see the ground because it was a bit tilted up. So it didn't map this environment. So it only mapped those environments that it could see, but it did recreate a very dense map of those environments. So what are the ways how we can augment this thing? So that is, as the Kalman filter is extendable, we introduce more sensing modalities that not only helps us get around this problem, but also helps us provide a visually degraded environment. Yes?
Are you using a molecular camera?
No,
or
this is a stereo camera, so we have a depth recreation. And one of the sensors that we want to introduce, or a different sensing modality, are the laser sensors. And Tung will be talking about laser sensors.
Thank you, Shehryar, for introducing me. So my name is Tung. Good morning, everyone. I would like to present another part of our system. That's a laser range sensor. It's very interesting and very challenging question we are doing in our lab. So imagine that our robot needs to operate in this kind of environment. So it's like kind of like dark environment. So conventional camera cannot work in this unless that we have to use some external light source to light up the environment, like Frank already mentioned before. So another potential solution is that we will use another sensor to compensate in this case environment. For example, in this case we use laser range sensor. So basically the laser range sensor here will provide 3D point cloud. It consists of many points in 3D environment. So basically one point here is provide us the X, Y, and the Z of point in environment with respect to the sensor frame. So in our lab, we are carrying out some research about in two directions. So we try to combine one kind of like short range laser sensor, like Flash and IntelliSense, and another kind that the long range sensor, so like Velodai and Hokuzu, that's my friend introduced before. You can see that naturally each sensor will come with advantages and disadvantages. For example, like in the case of short range sensor, we can get very lightweight sensor, so it's very suitable for aerial robot application. But in contrast, it's very short range and small field view. So we can extend to another more sensor modality like Velodai. It provides 360 degree in field view, and so it's very good for some application like robots or autonomous car that we are seeing nowadays, like Google car or something like that. On the right here, you can see this is 3D dense point cloud from Flash. I really love this picture. It's kind of like 3D selfie photo or something. And on the bottom left here, and bottom right here, we can see the raw point cloud from Velodai. So this when we drive a car outside, so we can get very long range this environment, so like more than 100 from the sensor. So how can we merge the point cloud? So basically, every time we acquire the new point cloud from sensor, we need write some algorithm to merge together to create a big point cloud, and at the same time we need to know both of the robot. So in robotics research, the dominant algorithm is that we call ICP, interrogative closest points. There's many steps involved here. I can explain briefly. Like for example, in the first one, we will get new point cloud from sensor. After that, because the point cloud here, for example, in our case, we have around 30,000 points, so it's not tractable for the computer to process the whole point cloud, and it's not meaningful. And that's, for example, we can see here, the whole region here is just like a plan, so we don't need to use the whole points in that region. So we develop some sampling methods to downsample the whole point cloud. For example, we can choose points randomly, or we can choose points uniformly based on our interest. Or another solution is that we can base on 3D structure of environment to choose some feature point that's good for next step. After we have sample feature point here, we will try to find logic points in compared to the previous point cloud. So after this step, we will have some kind of like a set of pairs like point from current point cloud and previous one. So and we will perform some optimization methods to estimate the transformation between previous one to the current one, or vice versa. It doesn't matter. So the optimization methods here, we are using some just popular like gradient descent or Gauss-Newton, or more advanced D11 but more work to robustify our optimization methods. As you know, that's the optimization method that we need to perform recursively. So we will try to estimate again until it meets some termination criteria here. For example, the overall error is smaller than some threshold, or the rate of the error is already stable, smaller than threshold. Or for example, if I said the step that computer like don't want to spend more time to estimate, so we can stop here. And finally, we will have something like this. It has 3D point cloud here, and at the same time, we have the balls of the robot here. One thing I want to emphasize that in this step, we want to find logic point between two point cloud, but we don't have any information to know about. Like for example, we have point cloud from this position and point cloud from this position. We not simply just assume that two point cloud align with each other. And in that case, if we don't have more information, we can run the optimization step here. We create some local optimal values. So it's not reliable data. It's not reliable values. So we have another solution is that we need some initial guess from point cloud, or we can combine with other sensor modality to try to get initial guess for the optimization here can achieve global optimal value. So in this slide, I would like to present the work that we finished recently. That we try to combine a VI system here that Shehryar mentioned before, and the small and short range sensor big flash here. So basically, in this work, we want to create some like denser map, more accurate and consistent. So given that we have two sensors, actually three, we have IMU. And given that we perform some calibration, like we use some standard package like to perform the calibration for the camera, and we develop some in-house software to calibrate between two sensors. So basically we already have on intrinsic and extrinsic parameter for this system. And I perform the same step I mentioned before. That's like we will perform the same link methods, and after that we perform the ICB here. But one challenging question here I want to introduce is that in this step we have something called condition number. Why do we need this step? Imagine that because our sensor, it has small field of view, so it might be trapped into some region. For example, we can imagine that a camera, the sensor face toward a wall here. So basically this region of wall is just plane wall. So the whole point cloud is just in one plane. So we cannot distinguish that whether robot move to the left, or whether robot move to the right, or whether robot stay in one place. Though if in this region we still perform the optimization step here, it will provide some optimal value, but it's not reliable. So we need to check this condition, some condition like this, before we apply the optimization step. So we call this condition number. We have some metrics for this. If anyone interested in this problem, we can discuss later. And in this case, if a robot trapped into some situation like this, we just simply use the prior information from the VI sensor to stick point cloud together. Again, so in this case, the 3D laser range sensor may be not accurate enough to perform the optimization step, but still we have some information about color of the world or something like that. So the VI still work in this case, so we can use prior information here to perform the final result. That we have a map and the balls of the robot. So I would like to show a quick video here. So in this work, we try to reconstruct 3D model here. Basically, we compare between the VI sensor along and the VI sensor with the laser range sensor. So you can see at the end, because the VI sensor, it has drift in the z-axis, so the table here will be like kind of 2 layers in the same point cloud. But if we perform optimization step with the laser range sensor, we can minimize the error in this case. Not eliminate completely, but we can minimize the error in this case. So if we add the better map, and the better map means that in the later part, when we perform the path planning or exploration part, we will get better result. So again, and we will try to like exploration the whole environment that I believe that Dr. Mascarich will demo in next hour in our arena. So it's the same like we use the VI system, but in this case it will create more denser map and a consistent map. So again, this is just a video that we perform the whole system here. We combine laser range sensor, 3D, the stereo camera, the IMU in the one system, and we create the map at the same time. We estimate the balls of the robot here. And okay, that's on for our part. Thank you so much for listening to us, and thank you Dr. Khattak Alexis and Dr. Mascarich organize this event. And personally, I would like to thank to Line Rose from SNC. He helped us a lot in last semester to do some work here. Thank you so much. If you have any questions.